There and back again, learning to simulate radar data for real-world applications. The long range and resilience of radar make it an important alternative to lidar and vision. However, complex noise artifacts pose significant challenges to radar-based perception systems. In recent years, data-driven approaches have made significant strides to overcome these challenges across a range of tasks in robotics. Central to the continuing success of such approaches is the quality, scale, and labeling of radar datasets, which in contrast to vision and lidar remain limited. Training models in simulation is a promising alternative paradigm, which is already being used extensively for developing sophisticated vision and lidar systems. To enable such approaches in radar, we aim to learn a radar sensor model capable of simulating realistic radar observations. In order to replicate the stochasticity of real radar in simulation, we use a deep implicit model to capture distribution of the possible power returns. We use a neural network to learn the mapping from world state whilst also learning how to replicate stochastic noise artifacts. We represent the world state as an elevation map. This allows us to easily interface with existing simulation environments without relying on specialized world models. We consider training our model using aligned pairs of real radar observations and partial elevation maps measured in lidar, alongside full elevation maps generated in simulation. To learn from real-world radar observations, we adopt an adversarial paradigm using a discriminator to determine between generated and real radar observations. To further constrain training, we also model the backward mapping. We introduce another discriminator to distinguish between predicted and simulated elevation maps. Learning the backward and forward processes side by side allows us to further constrain training through cyclical consistency losses and by encouraging the backward model to predict realistic elevation maps where labels exist, using the partial elevation maps generated in lidar. In order to evaluate our approach, we use our sensor model to train new models in simulation before deploying them in the real world. Specifically, we consider training a model segment the world into free and occupied space before evaluating its performance in the real world using the mean intersection of the union metric. Our best performing simulator is learnt minimizing the full training objective, encouraging alignment between real-world and predicted elevation maps alongside cyclical consistency. This allows us to train a model which performs only 4 percentage points off the same model trained on real-world data. Our simulator is inherently stochastic, capturing many of the noise artifacts that characterize real-world radar observations, such as speckle noise appearing as random fluctuations of power returns, saturation lines appearing as bright radial streaks, and ghost reflections arising as a result of complex multipath reflections. In addition, our backward model is able to infer the elevation of the real world with an average absolute error of around 21 centimeters. While slightly less accurate than a model trained to regress to partial height measurements directly, our model is able to better generalize to regions of space that fall outside of the range of lidar by learning from full simulated height states generated in simulation as part of our training setup. For more information, please see the full paper. Thanks for listening.